will be moderated by Band DL7APV. Everybody knows who is that. Everybody knows the largest 70 centimeters antenna in the world, and he will organize everything about our lectures in the last session. So, thank you very much.
No, it's not.
Hello, hello.
Ah, okay. So. I think we have to wait a minute. When the row on the coffee machine is a little bit shorter, we can start.
They will be silent. We have to follow up. We don't have a time.
Okay, next on the list is PA0HRK. Yes?
Silencio prego in the coffee corner, please.
It's after coffee break. Okay. Okay, Charlie is the next. We had mixed up here DL3 WDG, or better known as G3 WDG, reports on VS JTX on EME microwave, the hints and secrets about. Charlie, you have the microphone.
Thank you. Yes, good afternoon. When I first started putting this talk together, it was all based on QRA64. That was the mode of at the time that was showing the best performance. All with the 2-year delay to the conference, all that is now completely changed. And so the talk is mainly about Q65 and also the new echo mode. Because this is a very rapidly changing technology, I am attempting to keep this presentation up to date as there are more developments. And on your memory stick, you'll find in the file a link to updates to this presentation. And if you click on that, you should be able to download the latest version of this talk. This is already a couple of iterations further than you'll find on the memory stick, but the link should still be the same. So, Q65 and its features. I want to go through the choice of optimum submode and decoding options. I can see a signal on the waterfall, but I can't get it to decode. Why is that? And then getting the best out of Q65-60E for 10 gigs and above. There are a few radio-based issues and not just software that play a part in this. Then I'd like to spend a few minutes talking about a development to the echo mode, which is quite a significant advance over the version of the mode that is in earlier generations of WSJTX. Talk a little bit about Doppler compensation, how to determine the signal-to-noise ratio margin of a signal, and then if there's time, we can go into a few miscellaneous topics. So, just looking at the big, the bold points, how does Q65 differ from the previous QRA64, apart from having one more tone? The sync scheme has changed completely. So one of the user feedbacks to QRA64 was you couldn't see the signal on the waterfall hardly at all. But now Joe and team changed that, so it's a little bit more like JT65. There is a more pronounced sync tone, which makes signals easier to see. We've now got averaging brought back, so you can gain from having more periods averaged, and also some of us liked auto-sequencing, particularly in high workload situations where you can manage other things, not just have to keep interacting with the program. It's not a robot. You still have to make a significant user input, but it does automatically sequence the messages for you. It's more sensitive, and what's of great interest is a variety of different period lengths and tone spacing submodes. And it can also decode multiple signals in the passband, now cope with drifting signals, and allows the use of non-standard call signs with the same sensitivity as standard call signs, at least at one end. So for de-expeditions, you now do not have to suffer from being, having a prefix in front of your call sign, which is great. So what does a Q65 signal look like? Well, as I said, you've got a much more significant sync tone than in the past, where the sync was across all the symbols. Now, it looks then pretty much like QRA64 did, but you've got 25% of the energy in the single tone. And as with QRA64, you have to send to the decode frequency on the sync tone, and it will decode anything but within the width of the F-toll bar that you've set in the settings. So it doesn't look much different, but it's easier to see intermediate level sync tones. However, the things that interest us most are when you can see nothing on the waterfall at all, and yet it will still decode, and a little bit more about that later. This is a -15 signal, so it's huge, but it's better for display purposes. Now, one difference between between Q65 and a lot of other modes is, in the past, we've got used to thinking that the letter at the end of the submode, A, B, C, D, E, would relate to the tone spacing of the signal. That isn't true anymore, and this has led to a bit of confusion. For example, if you look at 30C, 60D, and 120E, these are all roughly the same tone spacing of about 13 hertz. Whereas if we were to look at 60D, it's 867, but the 120E is only half, roughly, the tone spacing. So you've got to remember that both letter and time are relevant in this. We'll see more about that and why that is later. And whilst the protocol has a 15-second mode, this doesn't work with EME delay, so you can't try 15-second mode except on experimental basis if you go into the code and make your own changes. So how to choose which submode to use? Two factors here. The longer period lengths increase sensitivity because you're transmitting the same amount of information in, for example, twice the time. And in fact, the tones are transmitted for longer duration. So basically, you've got more chance of the decoder being able to distinguish a particular frequency if the tone is on for longer. And so longer period lengths increase sensitivity, but, isn't there always a but? The narrower tone spacing associated with the longer periods means that there is a chance that the energy from one tone can spill over into the next tone's bin, and basically the decoder isn't quite sure whether it was, symbol 14 or symbol 15, in which case it starts to get a bit confused. However, the error correction codes can often sort this out, so it'll still work, but it may not be quite as sensitive. And I've just listed some of the commonly used submodes on the microwave bands. Almost all of them are 60-second modes. This is what everybody's been used to in the past with JT65 and QRA64. But don't forget that the other, there's a lot more that you can play with. So if you're having a difficult QSO, it will not go on 60D. Try 60E. You may be limited by the spreading. Or if the spreading allows it and you really can't make a QSO on 60E, then try 120E. And we've had a number of QSOs possible by going to the 2-minute period instead of the 1. So you're not stuck just to use what is the basic recommendation. And for very good reasons, we put the DL0SHF beacon on 60E, not 60D. Now, why is this? Shows a little bit more about why we need to be careful about choosing the submode versus the spreading. And what this plots is on the, here we have spreading, and here we have the signal to noise ratio at which you would get 50% decoding. So if you look at 60D, which is the red, you'll see that at 100 hertz spreading, you should be able to go down to about -25 and still get 50% decodes. But if you went to 120E, down at 100 hertz spreading, you'd be down to -27. So, 2 or 3 dB more advantage. A couple of interesting crossover points are, this graph was done really as part of the 47 gig research, whether to use 120 or 60-second periods. And you'll see that at 400 hertz spreading, pretty much all the advantage of the 120-second period length is lost by the tone spillover problem. So at 400 hertz, there's no difference between the sensitivity of using 60E or 120E, except that every period lasts 2 minutes and it gets quite boring waiting for the QSO to proceed, so there's no point. The other crossover point that is interesting is between 60D and 60E, and this shows that at about 70 hertz, below 70 hertz, 60D is better. Above 70 hertz, 60E is better. All activity on 10 gigs practically is on 60D, operating at spreadings of probably 200, 300 hertz, and you're paying about a dB and a half penalty in using 60D. But it's what everybody pretty much uses. So maybe a little bit of a rethink on what the best sub-mode is for 10 gigs. Most of the time it works fine and you'd never notice, but if you're really trying to get down to the lowest possible. What about other sub-modes? I've only put on graph of 120E, 60D and E. If you're really interested to find out how the other sub-modes work and how low you can go in signal to noise with them, included within WSJTX when it downloads is a program called Q65Sim. That allows you to generate wave files at any desired signal to noise and spreading. So you can do your own work without having to go on the air and experiment. And the simulator is very accurate, and it uses a very accurate spreading model for having the energy distribution to be similar to what you get in an EME signal. So more information on that's in the appendix. So, decoding options. You've got 3 basic: fast, normal, and deep. Most people either use fast or deep. What is the difference between them? Very little, Deep decoding takes longer, and for almost all of the time, you can decode the same signal to noise with fast as you can with deep. I think most of us who are scratching in the noise all the time use deep anyway, but very often a fast would have given you a decode in perhaps a quarter the processing time as it does with deep. One thing that not everybody's aware of is that if you are set to fast and you don't get a decode, if you double click back on the sync tone frequency and try another decode, it automatically will do deep for you. So if you didn't get a decode first time, try a double click on the waterfall and then a decode may appear because it used deep automatically. Or you can press the decode button and that will attempt another decode on the previous message. A little bit about AP. AP means a priori, which means that the decoder is fed with some information about what it thinks the QSO might contain in terms of call signs. And when you get a decode, at the end of the decode, you'll see Q0, 1, 2, 3, 4, and, well, if you use this one for specialist use, you can also see a Q5. But basically, this tells you what did the decoder get off the air. Now, if you call CQ and an unknown station comes back, you don't know who it was, it'll be a Q0 decode because it copied your call sign, the DX call sign, oh sorry, it'd probably be a Q2 because it knew who you were. You'll get Q0s if you're shortwave listening. If you don't have, if your call sign doesn't match the message, the DX call sign doesn't match the message, and you don't know who the grid is, and it's all decoded off the air, you'll get Q0. And then depending on how far the decoder has got, or how far the QSO has progressed, it's automatically loading the next information into the decoder, because if you're already working that station, you know that. So it helps the decoder by up to 4 dB. So more about that later. But it's happening under the hood, as they say. You don't need to do anything. The AP, if it can, is operating all the time. Now, if you are in a sked with somebody, you know who you're going to work, then if you should populate the DX call and the DX grid boxes with that station's information. That will help the decoder. All too often there's somebody on the logger, I'd like to work you, okay. So what happens is the person who they'd like to work calls CQ without anything filled in. The other station is then completely unknown to that call, to the CQing station, and the decoder's got to do all the work. Now, if you know that somebody's going to call you, or wants a sked with you, then don't call CQ and expect it to do all the work as well as it can do if you help it. If you've called CQ and someone comes back and decodes, if you double-click the decoded message, it will fill in the fields for you so that all parts of the QSO that are then happening will use AP. What happens other times, maybe you want to shortwave listen with the ultimate sensitivity. For example, it's a 47 gig test. You're monitoring, Klaus calling Al Ward, for example. So if Klaus is calling Al Ward, you have to type W5LUA in as your own call sign, and you have to put DL7YC and JO62 into the DX call and grid, and then you will get the same benefit of all the AP, and that may get the decode through that you wouldn't get otherwise. But do remember when you've done that, go back and change my call, otherwise you'll be CQing as W5LUA. and then you'll be a pirate. So the other thing then is using averaging. Again, this happens automatically if you enable it. So here we've got enable averaging checked, selected. We've also got auto clear after average decode checked. And then if it doesn't decode it, the message on the first attempt, next time the period comes along, this counter will say 1 in it, and 2 and 3, depending how many messages have been loaded into the accumulator. And often, the last 4 messages have equal weight. So in the old days of JT65, you had to be scrupulously careful to press clear average before, with a new station, or if you thought the message might have changed. Q65 is a bit more friendly. If you do nothing, then messages earlier than the last 4 are decreasingly ignored. So you can get away without doing anything, but it's better if you know things have changed, press clear average, and then the accumulator is clear, ready for the next message. And here's an example of an average of 2, where it took 2 messages to get that decode. This is from 47 gigs, and it was a Q3 because everybody had got the right call signs in as my call sign and DX, so the decoder was using all the help it could get. I'll stress this again, that if you don't check auto clear after average decode, auto clear average after decode, what can happen is if you achieve an average decode, then that accumulated information is stored. And if there's enough signal to noise by then in the accumulator, you can just add another message worth of rubbish, noise, or anything, and what will print on your screen is another decode, and that did not come from the last, it may not have come from the last message you received, and it can get very confusing. You can read this up later, but there is a situation where you don't want this checked, but this is a special case more related to 6-meter or 2-meter EME expeditions. But for us, this should always be checked or you can get confused. Right, so everything's great. We know how to work the program. We're on the air, see a signal on the waterfall, doesn't decode. Has this ever happened to anybody here? Or okay. So, little bit of a checklist. Firstly, are you sure that the other station didn't say 60E and you're on 60D? So a quick check on the logger. What did you say? Oh, sorry. I was on the wrong mode. Happens. If your QSO partner changes the message in the period, the bits obviously change. It can confuse the decoder. And next time round, it may be fine. It may simply be that 2 different messages got transmitted in the same period, and the decoder can make no sense at all of that. Possibly the other station transmitted too late, forgot to press enable transmit or something, and next time round it may be fine. More seriously, the signal may be drifting too much, or it may be unstable, and there are limits to just how much signal infidelity the decoder can cope with. Is your PC, this is the most common one, particularly among stations who are only starting, is the PC time correct? It won't work if you're more than a couple of seconds off true universal time. So the PC time has to be set correctly. It's used in synchronization of the signal. Can be that the PC time was corrected whilst you were in the middle of a period. Some people use dimension 4, and that's has a horrible consequence. It can update your PC clock by a second or so in the middle of whilst you're operating, and that will stop decodes. As I say, try deep code if using fast initially. There's a few more things here that can contribute, or there might be more than one thing happening all at once. But that's roughly what can happen. Moving on a little bit now, Q65 is the widest band, Q6560E. Some of the lower letter, shorter periods, but have wider tone spacings. But the signal bandwidth, this was a rig that we use, and you'll see the audio passband isn't really enough to pass the signal at all. So you will be losing upper tones, potentially both on transmit and receive. One fix for that is to use 700 hertz as the base frequency, which is why if you don't have 700 in the box and you're on 60E, it's in red. That's meant to be a little polite warning that you might want to think about changing to 700. So use 700 and you'll be better off. On transmit, you can compensate a bit for this slope by overdriving slightly at RF, not audio. So you can compress one of your driver stages or PA a bit, and that will flatten off the response at the top end. And in the early days of QRA 64E, we found it didn't work as well as we expected, but I don't think we understood these limitations then. Another thing that can help is the use of the reference spectrum. The function of this is to flatten the audio passband. It's available, there is a setup here of how to do it. I won't go through it now, but the procedure can result in, here was that passband before using the reference spectrum. After reference spectrum, it's flat. And we've actually gained some upper bandwidth. It's been able to compensate this gain slope. And why would you want to do that? Well, it can actually improve decoding because the upper tones are now getting through what was otherwise a rather too narrow passband for 60E. I mentioned 60E a lot because for 10 gigs, 24 and 47, it's the best mode to use, hence a little bit of focus on it. Now, I'd like to talk a little bit about the new echo mode. This is available now. If you go on the website and download the release candidate 2 of 2.6, you can get this new echo mode. What is different about it compared to the echo mode that was there before is this knows what the spreading of the signal is and integrates the entire echo power over that bandwidth to work out the signal to noise ratio. In the past, it was a peak search routine, but this is now doing a proper integration of the whole spread signal. So it can give you signal to noise ratio to within an error that you see when you run it. And we've done tests on it where the agreement, once we've worked out all the system parameters, we're getting agreement with VK3UM, which is really very close. It also, under controlled tests, produces the same signal to noise as a well set up Q65 decode. So we believe it's quite accurate. You can use it not only for own echoes, but you can also use it for measuring someone else's carrier. So for example, on 47, you can, if the signals are too weak to decode, one station can transmit a carrier at 1500 hertz, and this monitor mode will tell you, is there a signal there at all? And if there is, what is this level in the equivalent to 2.5 kc bandwidth? So it's really quite a useful tool. Also should be able to use it for system optimization. I mean, in the talks on feed matching to dishes and so on we've heard before is tweak for sun noise, tweak for moon noise. Now, with this, potentially you can tweak for maximum echoes. And so you're actually looking at the transmit and receive performance of the system all in one go. So This is an interesting tool. It provides a text output. So basically, there's the time that it took the echo. It's a 6-second cycle, just like the old one was. This is the number of cycles it's done so far, tells you your audio level. More importantly, it's giving you the signal-to-noise ratio. It's giving you an estimate of the error in that measurement, telling you how far off frequency you were, tells you the Doppler shift, and it tells you the width of the signal. These parameters are read from the Astro window. They're pre-calculated. They don't come from analyzing the signal itself, and the reason for that is it enables this to be more accurate and quicker. So you use it in exactly the same way as you used the previous echo mode. Here's an example of recent echoes with a 2.4 meter offset dish, 70 watts at the feed, 220 hertz. That's what the waterfall looks like, and this is what the echo graph looks like, showing you the width. Interestingly, there's enough signal-to-noise ratio to see almost all the signal from one limb of the moon to the other, as well as the center. Because as we know, the frequency of the signal is dependent on where it's come from on the moon, as we've been talking on 47. Well, the same is true here. Just a sort of what can you do with it as well. This was Bob, KA1GT, who's also been working a lot on the echo mode on 1296 running through thick trees, where normally you'd see no echo at all, but clear. He was able to, it's probably costing 20 dB because he gets about -9. And the signal-to-noise was coming out at about -29. So trees cost 20 dB, measured with one tool. So this is more detail on how to use it in the monitor mode. I don't need to go through this now, it's all in the file. But this is just, if you need to transmit a 1500 hertz tone, and these are ways of making sure that you, as the transmitting station, are truly transmitting 1500, because that is the frequency that echo mode works at. So there's an example of monitor mode. This was KA1GT monitoring us when we were running 1.2 meter dish with 70 watts. He was using just an 80 centimeter dish. So quite marginal systems, but nice clear echo and, reliable. Other thing I should also say is the Q column, which is the quality that has been assigned to how good the echo is, from 1 to 10, or 0 to 10. Even noughts can still be significant, can still be valuable information for very weak echoes. And here's an example of 47. This was before the guys got any decodes at all. This was recorded by W5LUA with Manfred transmitting 5 minutes. And this was the reported signal-to-noise ratio, totally random and all over the place, until by about cycle number 70, so about 3 or 4 minutes into the test, it had locked in and was starting to give good, pretty reliable signal-to-noise ratios. You can't see these signals on the waterfall, you can't see these signals with linear average, but this tool will dig in several dB below what you can get a decode and start giving you valuable information about, how well your equipment is working or what the path loss is or whatever. So there's a new release in the works. This is also able to use, you don't need to have a CAT-compatible radio even, because all the Doppler tracking is done at audio frequencies. So you can throw away all the complex radios and just run an IC202 or something, you can get very good results with this. It will also save wave files, so you can go back and play with them later. busy slide. It's just basically all the modes for automatic Doppler compensation. Most times everybody is using a CAT-compatible radio, and this is just the settings you need for it. Important to always use 6-character grids. On up to 24 gigs, I think the error in grid locator is about maximum of 10 or 12 hertz if you're at the wrong side of the grid. So really we'd like to have more accurate location information, but that isn't available yet. These are the equations for anyone who's interested in what's actually going on inside WSJTX, on how it's working out what the Doppler shifts are. And every Doppler mode has got a tooltip, so you can see which one does what. CFOM is very much the preferred mode now. You no need to know where the DX station is. They know that, and they're correcting that. Your own echoes are correctly tuned. Your QSO partner's signal is correctly tuned. You can monitor both stations in a QSO. For de-expeditions, it's brilliant because you can, if you're waiting to work somebody, you can follow the QSO progress, and then when you know that that QSO is finished, you can start calling. I think, and it's also ideal for random because you can just have a calling frequency like 10368 200 and call CQ, and if someone's monitoring that with CFOM, they'll appear. So it's great for that. Usage is nearly 100% now on the higher bands, and looking now on the 1296 logger seems to be that the majority of people are moving to CFOM now as well there. This is a tool built into WSJTX which allows saved wave files to have noise added to them. Why would you want to do that? Well, it's difficult enough to decode the signals in the first place. But you might be interested to know, was that signal 1 dB above my threshold, or was it 10 dB above my threshold? And the advantage of the degradation tool is that if you've recorded the files, you can go through them and add noise until it quits out. And again, information is there on how to use it. Q65 sync plots, that's fairly obvious. You can see here a trace of the, can't see anything on the waterfall, but you can see a trace building up on the sync plot. So useful. It's the only plot worth having for Q65. Newly added is drift compensation. So if you know a signal is drifting linearly, you can allow for that. It can correct for Doppler shift changes if one station isn't Doppler correcting, or if the station has drift. If the station drifts a bit up and then a bit goes back the other way, it's no good, but it works with linear drift. As I said earlier, you can now use non-standard call signs such as PA100 Talis or HA/G3WDG, and they work just as well as it did with a conventional call. You can decode the whole passband, and that's how to do it, but don't do that unless you want to, because it takes a long time to decode, but it can decode everything in your audio passband now. I will leave the appendix for you to have a look at, but it discusses the effect of delayed decoding. Did it matter that it took 3 seconds for the signal to decode before I started transmitting? And the answer is no, and this explains why, and a few other items there that you might find of interest. Thank you for listening.
Thank you, Charlie. Any questions? Al? Oh.
was in the title of the talk. I don't count 432 as a microwave band, so okay, but point taken. But pretty much everything applies.
That's not really my question. One of my questions deals with operating CW and WXJTX, okay?
Yep.
It's a problem for many of us to switch between the two. We have to shut off the WSJT. But what I do is, particularly on the lower bands, is I use no rig because otherwise it locks up on me if I go to CW and change the mode. Is there any way of adding a simple switch that can without losing the problem get back?
Right. This has been asked for before, and the objective or the response from the development team has been no. However, there are workarounds. And one of the workarounds is one that Zdeněk's used, and that is to have a small audio oscillator with a Morse key and feed that in as the audio input. And then you can transmit using SSB. System doesn't know that you're not transmitting WSJTX if you turn the internal volume of the WSJTX down. And you can transmit CW that way, or use a suitable Morse program that you can output through a virtual audio cable or something into the input. But it's a workaround, but you can make use of the Doppler correction facility, which is, you know, the great advantage of it.
Well, on the higher bands, this really isn't as much of a problem. On the lower bands, it is a problem. And that's another thing when you push for CFO on 1296, where you really don't need it because the Doppler shifts aren't usually that.
I'm not pushing for it. I'm observing what the users of the band are now doing. Nobody's been pushing CFOM on 1296. It's a movement that has, I don't know who started it, but it just seems to be happening. And I realize it's a pain in the neck if you don't have the CAT radio, but then...
That's not the problem. The problem is switching to CW.
Right.
Your solution doesn't really, or I'm sorry, the solution proposed doesn't work because when you're on CW, you don't want to use sideband bandwidth. You want to use your CW, you want to put the rig in CW so you can use the CW filtering and stuff. And that's what happens. That's when it locks up.
Right.
You take it out of SSB, and SSB is not optimum for receiving CW, quite honestly. So it's not so much, that would be another question, would be going back and adding the old CW mode to help people who are on WSJTX operate or use CW. This is a big problem. A lot of people would like to do it, but they have a difficulty switching. And the old system of allowing them to operate CW, though not ideal, at least gave them an easy way to start off
Yeah.
and do this. Okay, I have one more question. I'll get out of here. And that deals with the echo mode. In the old versions, there was an echo mode that continuously added, okay? You can go really deep below normal decode levels. And I found this very valuable in turning people on to EME. I get someone who has, you know, an antenna on the horizon, and they say, "Oh, I can't work EME." I said, "Well, try this echo mode because you'll see you're going to see echoes there. Now you need to improve things maybe to make a lot of QSOs, but you can actually see that echo coming there." And it had much greater capability even in this new echo mode that you're describing. It'd be nice to have another echo mode that you could give to people who are not so sophisticated that they could test their systems out.
Why don't you think the new one does what the old one does?
The old one used many echoes, so it could be not
infinite number. You can keep going as long as you've got patience. So it is doing exactly that. It is adding one echo to the next, to the next, to the next, to the next. And eventually a signal that you can't, I've got a demo on the laptop where it's after 20 echoes, then a signal starts to grow and it will appear. And it's doing exactly what you say. And with the release of release candidate 3, you'll have audio tracking. So you don't need a complex radio. It knows what the Doppler shift is. So when the echo comes back 400 hertz off frequency, it knows that, and it will shift what was 1500 hertz. If it's gone down to 1100 hertz, it will shift that back up to 1500 and add them all. And as the Doppler changes, it will keep piling it onto the top of the same 1500 hertz bin. So I think it meets exactly what you are saying, because it gives a beginner actually a chance to achieve some EME, which otherwise, is a lot more effort, and you get the encouragement. So I think the new one does exactly what the old one does. The advantage is it is giving you an accurate signal-to-noise ratio over any spreading bandwidth. So it's got that advantage, but it doesn't lose on what was there. Ian.
Entirely by coincidence, my question was related to the one that Alan has just asked, which is on the low bands in particular, how does the new echo mode react to the presence of fixed Verdi barriers?
It has, but we haven't yet tested this because unfortunately the testers only have 1296 and 10 gigs. There's one station who's been doing some 2-meter testing, but it has a dither mode, rather like the old one does, where it does a random frequency jump, I think of a few tens of hertz either side of the center, but I don't know exactly. And so the birdies will go down, whilst the wanted one, because it knows which dither it transmitted on, and it will bring that one into the accumulator. So I think it will average the birdies out, but okay.
I've got one question too, please, from chat about D4. You said that is not good for time synchronization. What do you prefer?
There's two options to that. One is use absolutely nothing at all, but set your PC clock up before you're active. But the one that everybody really likes is Meinberg, which is a continuous time adjuster, but it doesn't do it in steps. It kind of drags it in slowly and then maintains a very accurate time. Dimension 4 is okay if you don't, one thing people do with it is to set it to update the PC clock every minute. Yeah. And then of course every minute you stand a chance of having a crash decode. If you set it to 60 minutes or 24 hours, if your PC doesn't drift, you reduce the chance of this, false or lack of decode. Anyway, we are being asked to
Okay, thanks.
Stop now. So.
Yeah, okay. Thank you, Charlie, again. So, next one is Hake PA0HRK, low noise 100 MHz oscillators. Come on. And it's yours.
Thank you. So, good afternoon. Well, it's nice to have the opportunity to talk to you in Prague. By accident, I discovered yesterday that it was Christian Doppler who worked here 180 years ago and formulated his famous theorem that we all talk about, we think about at the university. So it's very by accident that I saw his house where he lived. Low noise, 100 megahertz, well, 100 megahertz VHF oscillators. Maybe it's a bit strange because we had so much tremendous microwave engineering today. And now I'm talking about VHF oscillators. But the relation is probably clear because all those microwave signals need to be generated somehow, and you might be using a VHF oscillator for that. Let me check out, yes. So this is the agenda I have. I hope you have some energy left for this talk. Well, the rationale is in fact that we see a lot of microwave synthesizers as in chip form nowadays, and it is beneficial. That has been proven by others, for instance in UKW-berichten and in Dubus, that it's beneficial to have a low noise oscillator as a reference around in the VHF area. So I will just take the next couple of subtopics fairly quickly, because I suppose you all know what we are talking about, but just to put it in the framework. What is phase noise, the effects of high phase noise, how do you measure it, and the starting point for my experiments with a VHF oscillator was the DG4KBF VCXO at 100 MHz, as published in UKW-berichten. I will present some measurements and some of my recommendations and construction notes, and some conclusion. And this is something wrong. Well, okay, this is all for today. That's what I'm doing. Ah, okay. It's a rocker. I didn't know. You don't know? No. Oh my God, now I have to tell a joke. Ah, there we are. Try again. No, of course not. I have 25 slides. Oh my God, this is the introduction. Yeah. Oh yeah, for sure. No? This is very strange, because I sent two files, and I sent a file another time, and they said, we received your second file in good order.
Look up. Maybe you can do something without the slides, talking a little bit. Okay.
Everyone here knows the principle that anything that can go wrong will, because it's EME practice.
Okay, we found a better one.
Hey, there we are. I have to be careful with this thing. So I was talking about modern synthesizer ICs that are very versatile, and but for higher microwave bands, the phase noise still lags behind the crystal multipliers, or it is roughly the same, but it's not extremely much better or something. But anyhow, you need a low noise reference signal. That is clear, and that is easy to show. Preferably in the VHF range. Normally you would say, okay, I start with 10 megahertz. but it's probably better to start with 100 megahertz or even 200 megahertz. And then you can stabilize that oscillator with 10 megahertz GPS or OCXO. We have heard about Morion, but any good oscillator can do the work. So what is phase noise? It is a random short-term instability of a signal. And there are noise skirts at each side of the main signal. And it is symmetric of nature. That's important because normally it's enough to measure only one sideband, one side of the signal. And normally AM noise has much less influence than phase noise, which is the reason why we and in general phase noise is considered and not so much attention is paid to AM noise. Well, what are important factors? You can imagine resonator quality, noise of the active element, other losses, and recently, I would say, the power source is also very important. Effects of high phase noise, I think we all know that. Desired signals are buried in the noise, and anyone active in VHF contesting will, in an rural area, will know that. External out-of-band signals may deteriorate receiving weak signals. For instance, radar and Wi-Fi signals can ruin our receiving capability. Noisy transmitters of other sources can disturb communication. And here we focus on VHF crystal oscillators as reference for microwave purposes, microwave synthesizers, but any other use can be imagined. So how do we measure phase noise? Well, in fact, there are many ways to assess phase noise. But in my practice, in fact, three ways are relevant. It is spectrum analysis, it is phase discriminator system, and cross-correlation techniques. Spectrum analysis, you do it with well, maybe not an ordinary spectrum analyzer, let's say with a good spectrum analyzer. And still then it is limited only to situations where the phase noise is pretty high, in fact higher than the spectrum analyzer itself. The phase discrimination is already much better. I myself, I have built a phase noise test set by DG4 RBF, also in UKW-berichten, but it goes maximum to 500 megahertz. And but the quality actually, the usefulness is actually quite high. You can already measure, so around minus 170 dBc in the per hertz. It should be, not square root hertz. And the third method is really the best method available actually. This is done in a complex instrument, for instance, FSWP, but there are others, and I will explain a little bit how these methods work and perform. This is a spectrum that I measured on my own spectrum analyzer. It's not even the best, it's the 62A of HP. And here we see a signal at 100 megahertz. And this is just about the maximum what the spectrum analyzer can show. Here we see, now I have to be careful, what is the button? This one? No, this is something else. What this? Yes. Here we see roughly the noise floor. And I know that this Wenzel oscillator, which is a very good oscillator, has a noise floor of about minus 180 dB per hertz. When I calculate what the noise floor here is, the bandwidth is 1000 hertz, so I have to subtract 30 dB to go back to a bandwidth of 1 hertz. The resulting noise floor is about minus 115 dBc per hertz. So it means there's a huge difference between the real value of this very good oscillator and what I can see on the spectrum analyzer. This is just to show that in this case the analyzer is useless. The phase discriminator is a lot better. It's a diode ring mixer based system, and it's followed by an ultra low noise, low frequency amplifier. You need a reference oscillator that can be phase locked to the oscillator under test. Could be seen as a limitation. You cannot measure every frequency you should like. The spectrum of the reference oscillator should normally be at least 10 dB better than the test oscillator. And they must be kept constantly on the 90-degree phase difference, which suggests a phase lock loop. Well, I made some mathematics just to show you that if you multiply a sine with a cosine, which has a phase difference of 90 degrees, you see a sine of the sum and a sine of the difference. And here we see the double frequency, and here we only see the phase difference. Well, I won't go all through the mathematics, it's pretty straightforward. But here we see that after filtering, because the double frequency will be filtered out, after low-pass filtering, we see a sine with the phase differences. And the funny thing is that if we take sine x for is x for small x, we find a simple expression. This gives us the phase difference, but it's a very, very weak signal. And well, that means that it is a challenge to amplify it so that we can perform some analysis, like a Fourier transform. I have a small picture. Here we have the oscillator under test. We have the reference oscillator. They are both fed to the mixer. We have the mixing products here. The low-pass filter filters out, of course, the high-pass. This is the loop, the phase lock loop. Here we have the ultra-low noise amplifier, and this is some way of analyzing the results. The ULNA, ultra-low noise amplifier, is, in this case, FET input, 60 dB gain, and its own noise is less than 1 nanovolt per square root hertz. The signal evaluation goes with a sound card and audio meter by DG8SAQ, which is very well known also from the small network analyzer. Which is a benefit of the system is that you can, for instance, see the behavior of a crystal. If you have a very stable reference oscillator and you have an oscillator under test with a crystal under test, then you can see the behavior over time of the crystal. You see the meter, where there is a simple discrimination meter, like old FM radio, probably you know. And you can see the wiggling of the meter, and then you know, this crystal is not perfect. It's a little bit difficult to build, but it can be done. And this is a result that I had from my phase noise measurement system. And it shows basically two sets of oscillators. One is the oscillator here at 14 megahertz. And this is just a test oscillator that I made myself. I made two, so I can lock them. And this is already a pretty good result. If you see that the noise floor here at 10 kilohertz is about minus 170 dBc, you have to translate this to dBc. It's a normalized amplitude axis, and this is a logarithmic frequency axis. And to be sure that the measurement is meaningful, it was confirmed on several occasions on a Rode and Schwarz measurement equipment. So let's for the moment trust this measurement. And to see how my FDM Duo performs, I made a measurement at the SMA output. And you see in blue, that is this line here, that that is the phase noise of the FDM Duo at 14 megahertz at the SMA output. And it's a little bit surprising to me that there is a plateau here and then it goes back again. We have to forget above 70 kilohertz because the sound card has a low pass at 70 kilohertz. But even then, you see a bit of a strange curve. I would more expect something like this, maybe a little higher, but not. It's a little bit strange. It gets even stranger if I stabilize the FDM Duo with a very good Wenzel oscillator. And then you see that phase noise is even worse. So probably, it's for sure, the stability is better, but the phase noise is somewhat worse. I think that the loop parameters could be improved, but I cannot look into the set, at least not in the software, so I don't know. Now we get to a little bit more complex measurement principle. That is the cross-correlation principle. I will just go through it quite quickly. But the crucial thing here is that you split the signal under test in two branches. And then again, you have two mixers. So it's split again. So in fact, you end up with 4 channels. And that's crucial to the principle, 2 different local oscillators with a different phase behavior, uncorrelated phase behavior. That's important. And so you end up with 2 I and 2 Q channels and a lot of calculation work. And then you can reach at a result at least 20 dB better than with just a phase discriminator. But it has a price that is probably even 40 dB higher, so that's little. But the result is very interesting. This is a screenshot of this machine. And on top, we see the correlation factor is 100. So we have, in this case, 100 correlations. The oscillator is a Wenzel oscillator. Again, it's one of the best oscillators commercially available. It's a Wenzel oscillator at 100 megahertz. And what you see here, this is the measurement result of the phase noise going to 1 megahertz. I can only measure to, let's say, 70 kilohertz, but this goes to 1 megahertz. So we have again here the frequency and here the amplitude correctly indicated as dBc per hertz. And what is interesting here is the gray area, because below the gray area the result cannot be trusted. As soon as the difference is about 10 dB, you can trust the measurement result. So it's a very advanced measuring system. And well, I'm very happy with this 100 megahertz Wenzel. So you could say here I stop, I have my oscillator. So, but well, that doesn't help anybody because the trick was how can you make such an oscillator yourself? So the starting point is the oscillator as published. It's a classic overtone design with a bipolar junction FET. It's also followed by source follower, which is a buffer amplifier with the same FET. We pay attention to noise, so we look what are the noisy components. Well, the FET has 1 over F noise, that's important. And we have thermal noise of the channel. And that's funny because it goes down with increasing ID, but it goes up with temperature. And if you increase the drain current, then the temperature goes up. So there should be somehow an optimization point. And it's also interesting to see that there is definitely measurable influence from the power supply. I don't know about you, but I remember many years ago that we stabilized microwave oscillators with a Zener diode, and that was considered sufficient. Not anymore. The crystal is also important, of course. I should mention that. On the other hand, I do not have a recipe for that. It's a fairly, still a bit of mystery how it works. I made VNA measurements on 20 or 25 crystals, and I did it as careful as I could, with a lot of averaging and a careful setup within resistors, how do you say that, attenuators and things like that to rule out any unwanted capacitors or induction. But it's pretty difficult. If you see a small series peak and a small parallel resonance peak and then some side resonances, well, you cannot always deduct, oh, that's a good crystal and that's a bad crystal. That's not so easy. So here I have to be a little bit fake, unfortunately. What I discovered is that the FET brand is important, and it looks like the onsemi SMD J310 is a very good candidate, and Fairchild is also a good candidate, but it's only new old stock, so hope to find some. But I would definitely recommend the onsemi, which is widely available and costs nothing. As I said, the design is very familiar. It's a grounded gate oscillator, nothing special, with a heavily damped drain circuit. Then we have some capacitance to feed the signal back into the source. We expect a low impedance here. Crystal has a parallel inductance to compensate for the holder capacity. You should not select that inductance too high, because then you risk to induce lower resonances. I have seen more than once a 100 megahertz oscillator resonating or oscillating at 60 megahertz. It's not a problem at all. So take this one a bit low. Here you see the Fari cups, which is necessary to close the loop for the control voltage. And it's important that the inductors must be real. Well, that sounds maybe a little bit strange, but I will explain in the next picture. And one of the things you have to take into account is the self-resonance. That must be as high as possible. And that's why I say the inductor must be real. And well, experimentation is required, but that is the hobby. To continue with the inductors, you see here small SMD conductors. And you see the wires. You see actually it's a wired part, component. And that's what you need. And I have also seen inductors, and they look like resistors. And these are, in our purpose, useless. For the rest, this is the oscillator. It is the standard PCB by the original author. But I made an important, I think, a small but important modification. I made pads for an SMD FET, because almost all the parts are SMD except for the FET, and it turned out that as the SMD FET is very useful, it is cheap and it works perfect, so I made provision to install such a FET. And here you see the power supply circuit. This is an LT3045. Originally, at the PCB, there was a LM723, but I did separate measurements, and an LT3045 with a very small low-pass filter behind it, 10 ohm, 1000 microfarads, and the noise problem is solved. Now, just a 100 megahertz oscillator, of course, is not enough. We always want a stable signal to be exactly on frequency. So we need a system to control the 100 megahertz oscillator, and we do that with a 10 megahertz well, whatever you think is feasible. You can use a GPS stabilized oscillator, but you can just as well until 3 centimeters for EME. Morion double oven oscillator is just as good, is my experience and of others. So we need the stability of the reference, the 10 megahertz reference, and the quality, the phase noise of the 100 megahertz oscillator. Well, we do that with an ADF 4001 PLL chip that gets its information. The registers are filled by a simple Arduino program. And again, to supply the charge pump here, I use an LT3045. Well, this is how it looks like. Whether it's beautiful or not is up to you, but it works really good. Here you see the VCXO, part of the signals being fed back to the PLL chip. Here we have the loop filter, from memory, the loop frequency, the cutoff frequency is 1 hertz or less. And I use an isotemp OCXO, but you can use whatever you want. Here you see the Arduino, and this is the LT35 voltage stabilizer. Well, this is the spectrum, the noise spectrum as measured on a FSWP, and to be honest, I'm pretty happy with it. This is the Wenzel oscillator, which is the golden reference, and this is the oscillator we just saw. And you see clearly the quartz of Wenzel is better. This is the part of the spectrum where the quartz plays a major role. Here we see the 1/f corner about, and here you see the noise floor, which is roughly the same. Well, just for your information, the data was from the FSWP. I took the CSV values and made some graphic in Octave or MATLAB. This is a prototype I made, and for one reason or another, it doesn't work so well. Well, I don't know why, to be honest. This is an SMD FET because I thought I need an SMD FET for best results. I can screw in any crystal. I can connect any crystal I want. Here we have the drain resonator. This is the buffer FET, and I go, this is the output via low-pass filter. But it doesn't work so well. I also tried to separate the oscillation function and the limitation function, because normally you do that in one, well, normally, but that's common practice, in one oscillator, in one device. So I tried to put a Schottky diode over the lower inductance in the FET, and but it doesn't work so well. Some details. I made, I think, almost 10 of these oscillators. For instance, this one is the original oscillator with an unknown crystal and with a jade routing. It works, but I will show the results in the next slide. This one is with a TQG, Telequartz group crystal. And my experience, Telequartz group crystals are pretty good. Even SMD crystals, there's not so much difference between SMD crystals and crystals in a larger base. The crystal I tried in Manhattan style doesn't work so well, and this one is also pretty good. Here we have the results of a number of oscillators. Well, we have seen how the the graph is composed, and we see that the blue one is a bit strange. Now, I want also to show some spectra on a spectrum analyzer. So I took a synthesizer, the ADF4351 standard evaluation board, and I tested the board with the internal reference on 1 gigahertz output, and it was on spec. So I decided to test it with a 100 megahertz oscillator. And first I took no, wow. What happened? This is a magic thing. Ah, thank you. So, well, that was good. Let me see. Have to be careful. Nah. I wanted to be careful. I don't know why stop. Just by this. I will not touch this thing anymore, and I will ask you, Zdeněk, to, because this is getting sweaty. Can I one sheet back, please? Number 22. Yeah. Here we see the standard ADF4351 board, which is definitely not the best synthesizer you can get. There are many better. But just to demonstrate the effect of noise on the reference to the end result. And here you see the generator that I used as reference because I need a noisy reference, otherwise I don't see anything on the spectrum analyzer. So I took my noisy reference, HP8664A, in the normal mode, and then you get this spectrum. And the funny thing is that you see the noise level at 3 kilohertz is minus 82 dBc per hertz. Can I have the next slide, please? Here you see what happens if you reduce the noise on the generator, which has also a low noise mode, on the left slide, by 20 dB. And the right slide tones the same setup, but with my own 100 megahertz low noise oscillator. And you see the difference is marginal. You cannot see it anymore. I have no idea if this is the bottom of the noise, say, of the synthesizer or of the spectrum analyzer. Next slide, please. There is no standard recipe for the 100 megahertz, but unfortunately there are some guidelines that you can follow. If you use on-semi 310, then I think you have a good chance to make a good oscillator. Real inductors, LT35, then you will end up with a good oscillator, probably. And a noise floor of minus 170 dBc per hertz is already pretty good. Well, to measure phase noise, you need a dedicated instrument, which is fit for the task. SMD design seems better than Manhattan style, but most of my measurements were done on SMD. And well, given the cost, you can decide for yourself if you take an ADF 5355 or you try a classical LO, which is multiplying steps, as an alternative. And the last slide you can see for yourself because that's only the some references. Thank you very much for your attention.
Yeah, many thanks, Hake. Any questions?
preferred JFETs because just from practice they give good results. Maybe a low noise VHF transistor is also a good option, but I didn't try it. First, because my starting point was different. Second, I have bad experience in the past because these transistors are prone to oscillation at higher frequencies. And FETs are much more quiet in that respect.
Ingolf. But
the drive power in the crystal? A little. I did it on 14 megahertz because then you can easily also measure it. I took a very small ring ferrite and you can make a current transformer. And at 14 megahertz I did it. I have not done it at 100 megahertz because on the other hand I thought a couple of milliwatt, which is normally too high, and I realized that. Normally you should limit to maybe 1 milliwatt. But to be honest, I didn't tell it, but I made an oscillator with 2 FETs in parallel. You increase the transconductance and you decrease the input impedance, which is better. But then the total output is also increased. But I didn't wait until the crystal breaks or something. But there is a risk, it's correct.
I think we have to stop. We are late in time. Many thanks, Hake. Thank you. And next, I introduce you Dominic, HP9 BBD, talking about 10 gigahertz polarizer. Bitte schön, Dominik.
Good evening, everybody. I hope you don't fall asleep because I think I have a very thrilling topic. Instead of the misunderstanding with Zdenek, I'm not talking about the polarizer because it has become obsolete. I prefer talking about power combiners for 10 gigahertz. I give it to you for inspection. Next. I don't touch this magic thing. Next.
Only one ham radio, which I know, doesn't use a PowerPoint presentation, only PDF.
Next. Yeah. Can you make it bigger?
I can do that bigger, but it will be on a half size.
Okay. You don't have to read. Usually, high power on 10 gigahertz is made by TWTs, which I don't have, which I don't want, because it's outdoor. High voltage outdoor is not my hobby. So I tried to do something much simpler, but effective. Next. This is how SP6 JLW makes his 300 or 400 watts, which was too heavy for me to have outdoor at the dish. So I wanted to have an alternative. Next. The traditional way to combine solid-state amplifiers is by so-called magic teas. And they are even more magic than the name would say. Of course, for 4 amplifiers, you need 3 magic teas, 2 by 2, and then again 1 to add. And they add the loss by number. And if you have 4 amplifiers, you have 3 magic teas, the expected loss is 20 to 25%. So 1 amplifier out of the 4 has become obsolete, which is too expensive and too sick. Next. Next. This is the traditional way. Here is the input network, the amplifier, and the output network. And you imagine how much copper, how many screws you need
to combine 4 amplifiers properly. And of course, all of these magic tees have an absorption load for the mismatch, to take the mismatch. I didn't want that. But the advantage of this design is you have full bandwidth, 5 gigahertz bandwidth. Do we need that? No. We need a few hundred kilohertz or maybe a megahertz. That's it. So this was not the solution I intended to build. Next. My first QSO with a 1 meter dish, 50 watt circular polarization at the time, which we have decided in 2002. And it was endless calling with those at 1 LPR. Finally, he called me, he received me, and I said to myself, that's not the way I want to enjoy EME. I want to be heard, so I had to increase power. Next. You know that indoor waveguide, the outdoor waveguide with the rubber sealing, and we don't need the whole bandwidth of these waveguides. Next. So, in the famous Orebro conference in 2016, I think, 2015, Goran, 86IW, said after his presentation, we should find out an idea how to combine solid-state amplifiers to increase power. And his solution was 5 amplifiers, and this was his design, how he would build it. And after a few years, reflection, it came to my mind that there was an idea by Goran. And I said to myself, I will do it, no matter what it costs, I will try to do it. Next. Next. So I omit all these heavy stuff, and I built this combiner. The question I remember, I think your article in Dubus where you mentioned that 50 watts may vaporize a bad SMA connector, which I didn't forget. So I tried out which connectors would fit. Sooner told me you may take N or you may take TNC. That's the thread BNC basically. And since this one is physically smaller and I don't have so much space, I decided to build a prototype with TNC connectors. Next. Again, this is the TNC. Next. The jumper cables, by the way, these Sucoflex jumper cables, they take 150 watts on 10 gigahertz easily. It was a risk. I didn't know how the outcome was, but I just wanted to try it. Next. Is it okay that we hurry?
Absolutely no problem.
Okay. So this is the prototype, machined by hand, not CNC at the time, machined by hand, the tuning screws here, and the 4 TNC input. This screw here is just for a reason of machining, not for any other reason. Next. This is the final layout, how I made it. And these 2 pieces which are going around are exactly with these dimensions. Next. That's the inside, 4 antennas on the input. And next. Since I have a network analyzer with 4 ports only, I cannot measure a single combiner with an input and 4 out, with 4 inputs and an output. So I had to build 2, connect them together, so I could measure with S11, S22 with 2 ports. First measurements were pretty promising. The impedance was reasonably well with 54, 51 ohm. And more important even, the throughput S21, S12, including the TNC to SMA adapter, was roughly 1 dB. So by half, it's maximum half a dB if we didn't count those. That made it very hopeful that it could work. Next. This is the bigger picture of the impedance here, and S21 and 12, forth and back, the same. And you see it's not 5 gigahertz bandwidth, it's just this little part which we need, and we get it. Next. Not sleep. Next. So to try out, I didn't want to try it out with high power amplifiers, so I built a little amplifier with 4 units all around this. These are A mode transistors inside, so there was a bit of heat, I think, I had to get rid of. So I built this one. Next. And importantly, I built switches for each of them because I wanted to see what happens when one would fail, when I switch one off. Because I thought when one is failing, I may kill the other ones or one of the other ones. So that was the setup, 17 dBm in, some loss into these 4 amplifiers. Here is the divider, amplifiers, combiner, attenuator, and test equipment. Next. Each of these amplifiers are measured isolated, just alone, and I got 36.68 dBm, which is 4.66 watt out, added all the 4 single measured amplifiers. In combine, I got 36.25, so per combiner, it was not even half a dB loss. Next. Of course, I tried 2 amplifiers as well, not just 4. I tried first the 2 opposite each other. It was a total shortcut. I couldn't make it work. So Eddie, ON7UN, told me, hey, take 2 adjacent to each other, which I did. And the result was even better. Per coupler, I got a loss of 0.16 dB. By the way, this presentation is not on the stick you have here, but I have the computer here, so I can load it for you if Oh, okay, it's on the website of, okay, super, thank you. So also the match impedance was pretty good for 2 amplifiers. Next. These are the phase shifter. The whole thing is based on proper phasing of the 4 amplifiers. Otherwise, it won't work. So you need to correct the phase by shortening or lengthening the input coax. This is one of these phase shifters, and you can see them here. And with this, you simply optimize the output power after the combiner. And with these screws here, of course, you can tune. And when you tune, the phase is again changing. So you have to do it around the circle various times, but you will find the maximum of power. Next. For the two amplifiers, I did the same. This is each amplifier isolated. 2.33 watt is 100%. After the combiner, 2.06 watt, 88.4% comes out, which is fine. Next. Next step was a bit more making my heart working, because after all, I thought, well, it may work. I took 4 Kuhn amplifiers, power supply here, and with 120 amps. So this became pretty serious, and I had shaky finger when I switched it on. Next. Again, the prototype here, input, divider, and then the next. These are the phase shifters. Next. Here you see the phase shifter at the entrance of the amplifiers, 4 pieces in a block. With these phase shifters, I can tune about 35 degrees, not more. So the cables have to be pretty much what they have to, so that I remain within the tuning range of the phase shifters. Next. So I tried with small power, with small drive. I tried it out, and happily, changing the power doesn't change the tuning. You cannot do this with TWTs, because changing power in TWTs is changing the phase, not in linear solid-state amplifiers. So what you can see here, the output combiner remains pretty much at ambient temperature. This is the load, the network to measure. If you take, I come back to Charlie, if you take marginal SMA stuff, you have a dummy load here as well. Next. This is the output network. Let's stay for a minute here. The dummy load takes 280 watts maximum, WR75 to WR90. Then the coupler, where I have 50.5 dB attenuation here to measure, and here comes the output of the combiner. Next. So the result was, instead of 50 watts, after all this stuff, was 250 watt out, with no flashing, with no shooting, with no smoke, nothing. Everything remains as designed, cool, and so I cannot complain. Next. This is the result again, same as before. These are the serial numbers of these 4 amplifiers, input drive for each, output, key down, bias current, and key down current. This is just single, every amplifier for itself measured. Next. This is what I got. This is input power in dBm. This is output power. So practically 230 watts is possible. It depends a bit on the temperature. So between 200 and 230 watt is usually possible. Maybe in summer it's a bit less. All has been made by 12.4 volt. I could go higher, I didn't. I wanted to be on the safe side because changing the amplifier would be pretty costly. Next. The efficiency. Power input is 1.14 kilowatt. Output 249 watt. So the efficiency 1.14 kilowatt divided by 249, 21.8%, which is probably feasible. Insertion loss is minimal, is marginal. Next. Practically on the roof behind the dish, here is the amplifier, divider. This is the 12 volt power supply for switching and so on. This is the power supply for the amplifiers. And yeah, sequencer, that's it. By the way, this is the beacon in Kiel, the DL0SHF, and this is my echo. So my echo is now pretty much as the beacon. Next. One of my neighbors complained she couldn't see satellite television, some channel when when I'm with the radio on. So I got on the flea market in Tristudne. I saw on the flea market this filter. So I measured it. I got use for it. Next. And here is the filter now. Next. And this is a sensational filter for me. The filter is like a mechanical filter in the shape, but the mode is changed from vertical to horizontal, and that's why they make it very much narrow. And happily, it's pretty flat. So I installed the filter, and when the authorities asked me about or told me that the neighbor has complained, I showed them this, and they said, "Oh, super." Next. It's possible to, in an easy way, in a very easy way, to combine solid-state amplifiers. However, we should be very prudent when we increase power in X-band. Thank you.
So, any questions? Okay. Thank you.
If somebody is interested, I have bodies, custom bodies for this. And I have the stretchers, phase shifters. Phase shifter you have? Yeah. You need? Okay. You give me 2 minutes.
I give you 3 minutes.
This is. Yeah, thank you. This is basically the intended topic by Stenek. It became obsolete because of this. Next. Next. Yeah, here. I do with the same station, I do tropo, rain scatter, EME. So I need to change the polarization. And so this is what my antenna can see. And with Italian stations, I do reflections primarily at Finsteraarhorn, which is 4,270 meters here. This is Finsteraarhorn. This is Eiger North Face, Monk, Pilatus. These are the mountains I can see. It's pretty much the same as Dan would see, I guess. Next. So I saw in Dubus that a guy made a polarizer by discs changing the orientation, and I did the same. This is a commercial product which is fixed. Next. So I machined various of these discs, and here is a screw which, when you turn, it takes the next all the time. And I wanted to be able to change 90 degrees. For EME, I should probably, as you say, change 270 degrees or something. I don't so far, but this is the concept. Rotatable discs. Next. That's how it looks like. It looks good, but it was not. Next. The return loss was very erratic. The throughput was erratic too, and the impedance was not satisfactory. Next. This guy, by the way, he died the day before yesterday. HB9 MPU, August 11, silent key. He told me, he is a very senior microwave man. He told me the edges on the long side of the waveguide, they create misleading RF into every direction, and it corrupts a good match and cannot be corrected. And I guess that's right. The result is a wild up and down of return loss, which obviously impacts insertion loss. That's exactly what happened. So the long edges inside the waveguide have to be rounded. Next. Here you can see I did it. Next. The result was immediately much better, but return loss was 20 dB, but still for RX, 20 dB for me is too much because I have a small dish. Dan could accept 0.4 dB and still it would work, not with my dish. Next. So this is now in place, but not with this bulky thing here. This is the rotator for the antenna. Next. My son has made the software because, as you may imagine, I'm not a software guy. Next. Next. There must be a better way to rotate the antenna without corrupting the quality of the receiving path. This is the solution. I enter here with the TX. Now, as you know, I have reasonable power, so I can accept 0.3 dB here by this flexible waveguide. It's a bend and twist waveguide. Here is the waveguide input. Here is the waveguide switch. And of course, next, at the waveguide switch is my homemade LNA. And as I found out with help of Mirek, I need some more gain here, so I have added another 12 dB here, and I can turn the whole stuff here together with the waveguide switch and the LNA because my transmit line is flexible. Since I make 3 times more QSOs than before. This is that's it. Thank you.
So the next and last session for today is from a nice trip. The expedition was from EW3HVB, and he will present his great expedition from TX7 EME.
Thank you. Thank you, Bernd. Evening, everyone. A little topic which is good for be the last one of the day, since I believe we are all quite tired now. How to plan a Middle Pacific solo the expedition and hope for the best. Okay, simply, I did my first the expedition, EME, the expedition on 2 meters in Tahiti, 2015. And another one, 2018, on Mauritius. You know, when you start doing this kind of things, it keeps growing on you. So you want to do it again and again. There was already a plan in my line of job to go back to Tahiti another time. So why not? But there are a few concerns. There were a few concerns, of course. And given that you are in the middle of the Pacific Ocean, those concerns are quite heavy to deal with. The moon windows are incredibly short towards Europe. Expect something around 40 minutes to 1 hour and a half at best. So not much time to work many stations. Air freight is incredibly expensive, can be as expensive or even more expensive than the airfare itself for one person. Since the inner islands flights are done with small ATRs or even twin otters, there's no absolute guarantee that they will carry all of your luggage with you. Of course, there's another problem. I would have been alone, so no other ham radio friend that could accompany me to handle every aspect of the expedition. So everything must be single-handedly manageable. I would have been forced to build the antenna, to assemble the station by myself, and that's it. Since we are in the middle of the Tuamotu archipelago, which is characterized by strong winds blowing almost constantly from the ocean, wind is a factor when you have a dish in front of the ocean. It's quite a factor. And of course, given you are in the middle of an atoll where it could be a problem to find some shampoo, finding spare parts for your station is absolutely impossible. So you have to be self-sufficient and redundant as much as possible within the weight constraints due to the air freight costs. Okay, the obvious choice would have been 23, but of course this led to some thinking. The moon windows, so you have to choose the right week not in the month, in the year. Because the combination between declination and availability is very, very difficult. There are only 2 weeks that allows you to have windows over 1 hour with Europe. So only 2 weeks per year. Suitable place, the shipping, the logistics is the true nightmare of this kind of the expedition. And that means, of course, a new dish and a new PA. Okay, Moonscad is a well-known software tool, and it's what I use usually to prepare for this kind of trip. I had to rescale the antenna from Mauritius because I had to do everything alone. So a 2.4 meter dish would have been quite complicated to arrange. Which radio to take, and then spare parts, SSPA and LNAs. Okay, the antenna, some very much needed characteristics. Must be light, but sturdy enough to sustain winds, up to 35 to 40 knots. Fortunately, I did encounter only a couple of nights gusts up to 30 knots. Usually it was around 20, which is not exactly a breeze. Must be manageable by one person. And of course I had this crappy rotator from SPX, which is not much robust. I had to reinforce it a little bit. But it was the only solution given the weight constraints. So it had to be working. And everything must stay inside a big golf case, suggested by René, Papa Echo 1 Lima. So everything must stay inside that luggage. So I rang Dad and told him, there's work to do. New antenna, new feed, and keep it simple, stupid. So I will be alone and I don't want to get crazy to build everything. Okay, these are a couple of simple photos. The feeder was one tricky question because we had to cut the flare a little bit, otherwise it would have been probably too much of a blocking given the small dish diameter, but it worked quite good. A new SSPA, I already built one for my home, but I built another one just to bring along in the expedition, using the well-known RF palette from W6 Papa Quebec Lima, and it gives very comfortably 500 watts without no issues at all. And I got a spare one too, so I brought 2 actually. Not complete, I got only another RF palette, tested of course, but I went to Tahiti with 2 PAs. Okay, in the other expedition I used my trusty K3 with the DB6NT transverter, but wanting to contain even a little more the weight, I did go for a 9700, which is quite okay, actually, better than expected. This is the place, Rangiroa Atoll, and I found a little guest house just in front of the ocean in order to have moonrise right at 0 degrees. It's quite a nice place, very quiet, not much people there actually. And that's here is the packing list. Just to give you, it's something around 140 items, and much of those are 10, 15, 30 items. So it's mandatory to have a very thorough inspection. Otherwise, just a simple connector can give you quite a headache. And I had to arrange cargo shipping from Tahiti to Rangiroa via ship because the air freight was simply unobtainable. And for a little, what did I do? Just a little trivia. There, no, up, 11, I believe. There. Any clue about this? This is one of the funny things about the expeditions. You have to find space where there's no space at all. That goes inside the septum field in order to have a double space also inside the feed. So that serves to protect the septum and the launchers, and you can fill up the rest of the feed with other stuff. Okay, so a little something very, very, very unusual. I have a video, I believe, here, just to. This is a small time lapse. Oh, you can just do play on the. Okay. This is just a time lapse of the dish assembly, which took one entire afternoon. I'm not moving that fast, you know. Lot of zip ties. Counterweight, which is done by a bag full of rocks. And here I mounted the feed backwards, so I had to dismantle it. Of course, when the last screw was on. Okay, that's the installation of the antenna. Okay. Okay, I had to tie it down at night for the wind. Of course, when here the moon is already over the US, so the window for Europe was already finished since probably 4 or 5 hours, actually. So the results of this small trip. The next one. I have it, actually. 93 QSOs. 93 QSOs, 82 initials, which is quite okay from there, given the conditions. Some CW initials, too. I did miss the WAC, because the only active station from Africa was from South Africa, and there was no common window. Okay, no, it was simply impossible to do a QSO. There was no common window with Zulu Sierra. Okay, just a few credits. Many helped with the expedition. The biggest thanks goes to my wife, because if you look at the luggage, the vast part of the luggage is ham radio dedicated. It's around 100 kilos. More or less. We're talking about 100 kilos. Again? Yeah, no, they were 3 actually, with my daughters. Okay, but of course Mr. Murphy likes to pay some visits, okay? So the very first problem was, unfortunately, the COVID-19 outbreak, which forced me to postpone the expedition, which was originally planned for 2020. And but the very, very incredible one is that the dish luggage was lost in Paris. So after the very first flight, fortunately I was able to recover it the morning after, and rushing from one terminal at Charles de Gaulle Airport to the other one, just in time to do the check-in for the intercontinental flight. Of course, one LNA did fail, unexpectedly, I should say, because everything is sequenced. And I have not been able to really grasp why it broke. Anyway, I had another one, of course, but next time I will take 3. So everything is never enough. So this is a simple and fast recollection of this trip. If you still are missing the QSL card, let me know. I have them here. So if someone is still waiting for it, we can amend that. Thank you.
Thanks, Giulio. Any questions? Okay, everywhere is hungry and thirsty, so I think we end here.
Okay, thank you very much. Giulio, it was beautiful, but I have one recommendation for next expedition. Your wife has to buy clothes on the place. Don't take more luggage. It is more simple way how to organize a good expedition, trust me.
You are forgetting something. I use clothes to make
I know the protection and packing of the stuff, yeah. It's perfect, but as I say, no more clothes. So that your clothes, perfect, or pyjama, that's okay, but no clothes. It's necessary to buy there. Okay, Jens, thank you very much for today participation on the lectures. I think that you had something interesting, you had something funny. You saw that also our technique and myself, I'm almost dead, so that I have to relax a little bit. About the dinner, at 8 evening we start the dinner, our gala dinner. When you will came in, I will be ready to start seriously at 8. Food is not available immediately at 8 because we have prepared some celebration. We have to spread some awards, we have to spread some presents and so on. After that, we will have completely the whole restaurant, including the food and drinks, under the midnight. So there will be plenty time. And you will be a little bit more hungry, and you don't leave so much food like yesterday on the place. So this is the one thing. Second thing, Volkmar has the QSL cards of the UR5LX, and UR5LX is presented there, and he help you so that if you need QSLs from UR5LX, they are there. OK 1 Kilo India Radio has plenty of the QSLs which they would like to give you, so that Tonda is sitting here and Tonda has QSLs. This is for the organization. Tomorrow we will start according the program. I hope that I will be able to wake up that Sunday morning so early. And we will see each other on a gala dinner. So thanks very much, and see you approximately 1 hour, 15 minutes. Jo, okay. Já jsem tu svoji prezentaci trochu vylepšil, takže já to pohodě. Yeah, I know. I think